What if I told you that there's one neat trick that you can use to guess the correct formula for almost any physical situation? A trick that'll not only get you the right answer, or at least close to it, but can also help you understand how all the pieces fit together. The story of calculus is very much intertwined with the story of physics. After all, calculus was invented as a way to solve problems relating to our physical world. Now, anyone who's taken a physics class probably remembers having to use a lot of different formulas, involving things like distance, time, force, energy, all sorts of different quantities. And it can be kind of hard to keep all those formulas straight. But there's an easy way to figure them out if you don't remember them. The secret is to use units. Yeah, those things that your teacher always told you to put at the end of your answer whenever it was a word problem. But there's a lot more to units than just bookkeeping. We can use them as part of a process called dimensional analysis, in which we look at how those units are related to each other in order to gain insight into how the quantities themselves are related. Here's an example situation. Suppose we drop a ball from 60 feet in the air. How long will it take the ball to reach the ground? Now, you might remember that there was probably some equation for this in physics, maybe involving distance, time, gravity, some powers and roots, but you might not remember exactly what it is. Well, with dimensional analysis, we'll be able to recover most of the formula just by seeing how the units play with each other. Now, what do we mean by dimension? A dimension is just a quantity we can measure in the physical world. And a lot of things in physics, mechanics in particular, can be broken down in terms of three basic dimensions: mass, length, and time. There are others like temperature and electric current in other parts of physics, but we're just going to focus on these three for now. Now, each dimension can be measured in a number of different units, which you use in your everyday life. So, for example, meters in the metric system and feet in the imperial system are both ways to measure the dimension of length. From there, we can combine these dimensions and different powers to get other quantities we care about. Things like area and volume, for example, are just powers of length. We can also use negative powers to divide by a quantity, like when we divide by time to get certain rates. For example, velocity is distance, or length, traveled per unit of time, like meters per second or miles per hour. So time gets a power of -1. Then acceleration is change in velocity per unit of time, like meters per second, which we usually write as meters per second squared. So there, time gets a power of -2. And that's just the beginning. Lots of other mechanical quantities such as density, force, and energy can be found in this way. And they all have a variety of units we often use to describe them in different applications. Now that we've seen what dimensions are, let's look at how to combine and compare them. We have three basic rules we can use. First of all, we can only add or subtract quantities if they have the same dimension. For example, 3 feet plus 4 feet is, you guessed it, 7 feet. Actually, it's even okay to combine different units of the same dimension. I can say that my height is 6 feet and 2 inches, and that still makes sense because both are units of length. Though you'd have to convert them to the same unit to do any arithmetic. But if I ask you, what's 3 miles plus 4 days, you'd probably look at me kind of funny, because it doesn't make logical sense to add length to time. By the way, notice that we're using these square brackets to denote dimensions. We'll be using this bracket notation pretty often, though a lot of the time we'll use it for specific units like feet, instead of dimensions like length. Our second rule says that when we multiply or divide two quantities, we multiply or divide their dimensions. For example, if we divide the number of miles in a trip by the number of hours it takes, we get our average speed in miles per hour. This is also what allows you to do unit conversions like you might have done in chemistry class. Finally, our third rule says that whenever we compare two quantities, like in an equation or an inequality, the dimensions on both sides of the comparison have to match. That's going to be useful when we try to figure out an equation relating different quantities together. Okay, let's look at our ball. We'll start by identifying some different quantities of interest. We want to know how long will the ball be in the air. So we might ask, what does that depend on? Well, it certainly depends on how high the ball is off the ground, and it also depends on acceleration due to gravity. Looking at the dimensions of each, time is just time, no surprises there, and height is just length in the vertical direction. And as we said earlier, acceleration has dimensions of length per time squared, or LT to the negative 2. Next, let's write time as a generalized product of all the other variables. We have an unknown power of height times an unknown power of gravitational acceleration. We'll figure out those exponents in just a moment. We also might have a scale factor k, which is just a raw number that doesn't really factor into the dimension. Think like the pi in pi r squared, or the 1/2 in 1/2 base times height. We'll discuss how to get that part later. Now, since we have an equation, the dimensions on both sides need to match. So we can use our basic rules of dimensions to break it down into its individual pieces, and then substitute the dimensions we know into the equation. Since our scale factor k is dimensionless, we put its dimension as 1, so it doesn't end up factoring into the equation. Let's clean this up a bit using what we know about exponents. We can distribute the b over to the LT to the negative 2 by multiplying the exponents. And then we can combine the two powers of L by adding those exponents. So what we end up with is the L's and the T's neatly collected together on each side of the equation. Alright, let's match up our dimensions. We'll start with time. We've got time by itself on the left, which is really time to the first power. That has to match t to the negative 2b on the right, so negative 2b must equal 1, which means b equals negative 1/2. Okay, how about length? Well, we have L to the a plus b power on the right, but there's no L on the left. Well, really it's hidden. We can actually write L to the 0 on the left, and since anything to the 0 power is 1, it doesn't really factor into the equation. That means that a plus b has to equal 0, and since b is equal to negative 1/2, a has to be positive 1/2. And that's it. We can plug those powers into our generalized product, and if we remember that a 1/2 power is actually a square root, we can clean it up just a bit more and say that the time it takes for the ball to drop is proportional to the square root of height divided by gravitational acceleration. And we're done. Well, almost. How do we figure out that constant k? See, dimensional analysis only gets us so far. It can't actually tell us what k is. So really we have two options. On one hand, we could try to reason out what k should be, maybe by applying some things we know about the situation. On the other hand, in the real world, we might not be able to reason it out, because maybe we're investigating something brand new. In that case, we might run an experiment, collect some data, and then try to gain some insight from what we find there. I'll go ahead and tell you that in this example, the correct value of k turns out to be the square root of 2. So that puts a 2 inside the square root. When we talk about motion and integrals later on, you'll see where that 2, or root 2, comes from. But dimensional analysis still got us 90% of the way there. Okay, we've got our formula, let's go ahead and solve our problem. The ball was 60 feet off the ground, and the acceleration due to gravity is 32 feet per second squared, so we end up getting a time of just under 2 seconds before the ball hits the ground. By the way, our formula actually works no matter what our units are, as long as they're consistent with each other. If we were to use the equivalent height of 18.288 meters, we'd have to use 9.8 meters per second squared for gravity, but we'd still get the same answer for our time in seconds. So the main takeaway of this is that understanding the units can help with understanding the mathematics. One of the best ways to make sense of math is to link it to the real world, especially when it comes to calculus. So remember to pay close attention to units. Think of them not just as something that gets tacked onto the answer, but as a fundamental part of what's really going on behind the scenes.